Good afternoon. Welcome back to Krishna's classroom. It's after a brief recess due to some flooding problems that I am resuming this talk. And we continue from where we started or where we stopped last time. In fact, you recall we were building up a narrative on the paths that we have taken from Riemann to Lebesgue, justifying the reasons for pursuing such a path. And in fact, we have concluded last time the process of integration, at least not moving everything because which has been done in a series of lectures earlier, just a brief outline of how you modified Riemann integration to get the Lebesgue integration. And naturally, the question that comes out is this: have we gained something from this exercise? Because it has been a very fascinating, long exercise to reach from there to here, and it took enormous number of years to evolve these ideas. So the question that automatically comes is, have we got rewarded for this? First of all, what do we expect? We expect a larger class of functions than Riemann integrable functions to be amenable to the new integration theory. That's the first thing. At the same time, it should be a genuine extension of the Riemann integration, in the sense that if a Riemann integrable function is there, then its Lebesgue integral, it should be Lebesgue integrable, and the Lebesgue integral should coincide with the Riemann integral. This is what you mean by a genuine extension of this idea. So let us verify this. After all, we have gone through the process of integration. So still we are at large, whether we are what class of functions are come under this new integration theory. And in this regard, it has been extremely gratifying that we have made tremendous progress. And in fact, eventually you will see that we have achieved what all problems that existed, or we have achieved the correction of, or we have improved upon the problems that we have had with the Riemann integration. And the new class of functions is a genuine extension of Riemann integration integrable functions, and the integrals do coincide, and also the extra class of functions serve our purpose. So it's far more general than the Riemann integrable class of functions. Now this is the outcome of the whole thing. So the exercise was worthwhile. Okay, so now let us look at the results which deal with this. Now recall that we had the following result for Riemann integration. What are the Riemann integrable functions? Let us recall. What functions are unintegrable? Now, in the modern language, the newly crafted language of Lebesgue, of sets of measures 0, etc., we can restates the result, and this result is due to Lebesgue. So we have the theorem, the following characterization. Gives the result, or rather identifies the Riemann integral. And this theorem is due to Lebesgue. And let me write this. Let f be a bounded function on a compact interval contain. It's important that it's an interval, it's compact by which we mean it's closed and bounded. That is the characterization of compact intervals. Okay, then f is Riemann integral if and only if, that is the characterization, if and only if the set of points in AB at which f fails to be, f fails to be continuous as this is of course expressed in the new language of measure. In fact, we are looking at the sets, the points of continuity. For instance, you take monotone functions on this interval, then you know that it's the set of discontinuity of such functions is countable, and all countable sets have Lebesgue measure 0. So you see that all monotone functions are under this class. To take all functions of continuity, they naturally come under this class. So you see that a large class of functions which are Riemann integrable. So if we designate RAB, the set of all Riemann integrable functions then it is a huge class. In fact, CAB, the set of all continuous functions, are A. So also if you take all monotone functions, on the closed bounded interval AB have at most countable set of discontinuities and every countable set has measure 0 with measure 0 and hence belong to so already RAB is very rich. Is a huge class with most of the desirable functions that is not the problem. Only when we started looking at further structures of this and further properties of this, I think we thought that possibly we need a rethinking on Riemann integration and introduce an improved version, an improvement on the Riemann integration theory to accommodate some more desirable functions. Okay, and that's why we did such a elaborate exercise for that. Now the question that you ask is, can you get all the Riemann integrable functions Lebesgue integrable? So we look at all Lebesgue integrable functions, which is the new integration which appears in the wake of the new integration theory that we have developed. And you want to ask this question: is Riemann integration all Riemann integrable functions Lebesgue integral? Further, do they have the same integral? Is the Lebesgue integral of a Riemann integrable function the same as its Riemann integral? So these are the two questions that we would like to have, so that we would have obtained a genuine structure. So let us now use the notation for such functions and then try to build the. Rather, I am not going to prove anything here. I would rather state the theorem and then possibly make some remarks about some examples. So let designate the class of Lebesgue integrable functions defined on okay. So the first thing that you have improvement that you got is E need not be a interval. Okay, that's the first thing. Okay, here we are Riemann integration we developed only on functions defined on intervals, whereas here we have got out of that constraint. Okay, and you see that E could be a interval also, right? Then we had the following characterization of or analogous theorem that we had for Lebesgue integration, and this was because there were two things that we observed. See, even Lebesgue integral, Riemann integral, if you carefully analyze, we partitioned the domain of the function and then constructed step functions and then approximated the, and we were only talking about bounded functions on this interval. Then we were approximating it from below and from above. And then for these functions, it is easy to define an integral. And then you prove that if these conditions are satisfied, whatever is stated for characterizing the Riemann integration satisfied, then you can approximate it, or you have the lim sup and lim inf of the lower approximations and the upper approximations respectively, and this would be equal under those conditions. Okay, so that it is Riemann integrable. So now we have a similar approach here, but now the whole thing changed. Okay, we are now talking about a new class of sets called measurable sets. Okay, which need not be intervals. So, and we again work on what we call simple functions, which are nothing but the step functions defined on such sets. Okay. Once again, we have the concept of measure. Therefore, a similar technique is adopted to get a lower approximation and an upper approximation when you are taking bounded functions, and so on. Okay. So it's a similar process that we. So let us recall one of the nice results that we have, or sort of reworking the criteria for Riemann integrability here, which we make use of. Let psi and b sequences of functions, each of which is integrable over E such that the sequence phi n is increasing and the sequence psi n is decreasing on. So these are integrable functions. Let f the function. In fact, we work with extended real valued functions. But for the time being, let us work with this. I will make some remarks on that. The function f on E have the property that phi n is on E. So this is the criteria, okay, for every n. Now what we do is we look at these functions. So you are approximating from above and from below. Okay. So look at the difference of these two functions, because you know that phi n is less than or equal to phi m for any m n and m. Okay. If limit n tending to infinity of integral or rather we will take because then you don't need, because automatically sin n minus equal to 0 as n tends to infinity, then pointwise almost everywhere on and f is integrable over with limit So this is the whole thing has been translated into more workable form. So given an f on E, our job is to investigate whether it is integrable, Lebesgue integrable or not. Our job is, if possible, to construct a sequence of an increasing sequence of functions phi n and a decreasing sequence of functions psi n, where both phi n and psi n are integrable over E, and such that this inequality is true on E, so that, and further, these functions are so constructed. Now, this is the important thing. This property has to be true. That is the difference between, see, it is something like this. Suppose you have a function like this. Now, you are approximating from above. And just give me an example. I mean, it's not. And from above, you have another approximation of the same kind. This is here. Okay. So, you see, these are two approximations that you can think of for this. One from below and one from above. So, this is the white thing that you see here is your, I don't know whether it is visible as white thing. All of them may be visible as white thing in screen. I don't know. I have no idea. But you see that this is your function f, and this is your psi n, and this is your phi n. Okay, and then the difference between these functions at each point, you get a new function psi n minus phi n, which is a non-negative function. And you see that integral of this over E, because this is going to be integrable because both psi n and phi n are integrable. Therefore, their difference is integrable. And that will be a function of n. And as n tends to infinity, the limit of the integral should go to 0. If that happens, then what happens is that these functions, these approximating functions, approach the function from above and from below, so that eventually it collapses into the given function. Okay, and the integral correspondingly converges to the integral of f, or f becomes integrable, and the integral of phi n or integral of psi n both converge to the integral of f. This is the whole idea. Okay. So the question is, do you have such functions existing? If it is there, then you are done. Okay. So that's a much easier thing to work with, if that is possible. And then you have the following theorem eventually. That is, this is another characterization theorem. Yeah, I want to make another remark. Another remark is this. See, whatever happens on a set of measures 0 in this context will not matter. Why? Because you can take that set of measures 0 out from E and get a new E tilde. And on E tilde, if all these conditions are satisfied, then everything is fine. Because the integral of f would be the integral over E tilde plus integral over the set of measures 0. The integral of the set of measures 0, no matter what value the function takes, or because you are talking about in the extended real valued functions, it may take infinite values. Does not matter. We have the calculus prescribed as 0 into infinity equal to 0. Now this is at the crux of it. And therefore, whatever we do on a set of, whatever failure of these conditions happen on a set of measure 0 is not immaterial. Okay. So right. So let us now state the theorem. So the characterization theorem. This is under two conditions. One, E is a set of finite measure. Okay, so E cannot be the whole of R. E cannot be the half line. Okay, so E cannot be a set whose length is or whose measure turns out to be infinite. Okay, so what we need is the domain E should be such that the measure of E should be finite. Okay, so this is the criteria. So we are looking at only functions defined on E. R star is a real value function. Measure of E is measurable and measure of E is finite. So this is the criteria that we have. Further, what more is required? F is bounded. We state for E because we are not we have already discarded the set of measures 0 on which the function takes the value possibly plus infinity or minus infinity. Okay, that we have completely removed, and after that whatever remains is what you hold. So you have E is this equal to E tilde, the function defined on this. Okay, so this is the set of measure 0. Here the function can take value. So we eventually work with a set where measure of E is. This is the case. Okay. Now what more? We assume F is bounded on. Okay. So for bounded functions, so that means they are real value functions, obviously. So I can, in the statement of the theorem, I can drop this because we have already filtered out the classification. Okay. So let me state the theorem. I'll give you a new page. Theorem. Let F be a bounded function. A bounded function on a set of finite measure. So the conditions are it should be bounded and it should be on a set of finite measure. Then F is Lebesgue integral. over if and only if it is measured. Very, very generous condition that you have for these functions to be. Okay. So f belongs to this is this condition. Now you see that we can easily prove that all Riemann integrable functions are measurable. Okay. All continuous functions are measurable, all monotone functions are measurable on, I'm talking about bounded intervals. E is equal to AB if equal to a compact interval AB. Then all is a set of measurable functions, and therefore this is an immediate outcome. Which means all nice functions that we have got into the Riemann integrable class are now Lebesgue integrable. And then you can also show that the Lebesgue integral of a Riemann integrable function is equal to the Riemann integral. So if f belongs to then let me tag this with R Riemann integral. Talking about Riemann integral of f is equal to, write this here, Riemann integral. This Lebesgue integral of f. The two integrals to coincide. Therefore, all Riemann integrable, all are Lebesgue integrable, and the two integrals to coincide. Therefore, what we have achieved is getting a genuine extension of the Riemann integration. This is a nice characterization here, and you can compare this with this. See what happens is, here I am not assuming E to be an interval. That is one. In fact, all bounded intervals are sets of finite measure. Okay, so I am not assuming that for this theorem, we are not assuming that it has to be an interval. So we got rid of that restriction. The second restriction that we get rid of is this, that f is bounded on a subset of E whose complement has measure 0. Okay, so it's almost everywhere it's a boundary. Then this integral. So you get a very large class of functions. Well, on Riemann integrability, you are talking about the discontinuity. Here also you are talking about the discontinuity. But the discontinuity is now allowed second, level discontinuities. Not the first type, but the second type of discontinuities you allow. So get a huge leap forward from Riemann integration. Now we have to explore whether the leap forward that we have already obtained serves our purpose. Namely, we are looking forward to many more nice things to happen, so that one can do analysis on the Lebesgue integrable functions comfortably. And what I am referring to is the completeness property of the space analogous to RAB. That is LAB with L1 metric. In fact, we achieve much more as we shall see. So I think this is one problem that we have already obtained. We got a characterization. We now get a feeling for those functions much better than before. Now what more we look forward to is how the Lebesgue integration is an antiderivative. Okay. So the connection between derivative and antiderivative expressed by way of what are called the fundamental theorems of calculus. So this is something what we want to look at next. And then eventually, of course, the L1 space or LP space that we have and the completeness, all the details we have worked out in our series of lectures, but now we are just recalling it. And then after that, we go to generalize this idea where we are no more constrained to work on functions defined on R, but we would take a great leap forward that it could be any set. And if it has the desirable structure, then on that you can define a measure, and on that you can meaningfully recraft the integration. Now this is all. Thank you very much.